Our next presenter is going to be Chen Almagor. Is going to be presenting on you say factorization machine, I say neural network. It's all in the activation.
Thanks for the introduction, and hi everyone. I'm Chen Almagor from the Hebrew University of Jerusalem. I will present our work FIFA. You say factorization machine, I say neural network. It's all in the activation, which was done together with Yedid Hoshen. Interactions between features play an important role in many classification tasks. One of the simplest ways to model the second-order feature interactions is to learn a dedicated weight for each pair of features. From all these weights, we obtain the interaction matrix W. W is a symmetric matrix in which every entry holds the weight that is learned to a pair of features. The problem with this approach is that estimating W is hard due to its huge dimensionality, and there is usually not enough data to estimate the interactions directly. And this is where factorization machines model come into play. This model learns the effect of feature interactions by low-rank factorization of the interaction matrix W. Followed by this model, field factorization machine models have been proposed. For example, FFM, FWFM, and FMFM. These models are based on the factorization idea, but also add an explicit modeling of the field information. An important observation is that all the factorization-based models are generalized by the following form, which contains an embedding vector for each feature and a dedicated matrix for every pair of fields. The choice of this matrix determines the recovered model. For example, if it's an identity matrix, the basic factorization machine model is recovered. The ability of deep neural networks to learn feature representations on other modalities has led to efforts to combine them in tabular data, in tabular tasks as well. Wide and deep models have been introduced, which are models that integrate the architecture of factorization-based models and deep neural networks. Blondel et al. Have shown that factorization machines can be formulated as polynomial networks by employing a quadratic activation. We extend this connection between factorization machines and neural network much further to include also field factorization machines and wide and deep approach. We propose a single neural network-based framework, FIFA. FIFA is formulated as the expression above. It gets a pair field input vector XF, passes it through a pair field factorized networks phi, sums over all the resulted field representations, then an activation layer sigma, and final nillinear layer. The framework is characterized by two main components, the adaptive activation sigma and pair field factorized networks phi. Let us state a lemma. Both modern factorization-based models and ReLU networks can be represented in FIFA's formulation. This lemma means that for recovering factorization-based models or deep neural networks, we should set the pair field networks to be a low-rank pair field matrix and control the recovered model by changing the activation. For factorization machines models, we set the activation to be a quadratic activation. For one hidden layer neural network, we apply a ReLU activation. And if we ensemble quadratic and ReLU, we obtain a model that is equivalent to wide and deep, up to the depth, of course. The bottom line here is that FIFA can switch between popular methods by simply modifying its activation. The question now is how to choose the activation function. So there are several approaches for finding the better activation for the problem. One approach is to search over both activation functions. The disadvantage is that another hyperparameter is added for the hyperparameter search. Second approach is to ensemble the two activations together as done in wide and deep models, and let the model degenerate the less effective activation and direct the parameters to the better one. The downside is that it doubles the number of parameters. Our approach is to use a nonlinearity that automatically adapts according to the task. We suggest using GLU activation as such adaptive activation. Above, you can see its definition and graph. We found it very attractive because it combines ReLU and quadratic activation. We can see that around 0 GLU behaves approximately as quadratic activation, and outside this neighborhood, it behaves as ReLU. Therefore, by scaling the magnitude of the inputs for the activation layer, we can adapt to the better activation of the two. Another key component in the framework is the per-field factorized networks. We found that the learned field representations should be of high dimension, but this requirement increases the sample complexity. Therefore, we suggest to employ the structure of field-wise factorized networks. That means that the input of each field is passing through a dedicated two linear layers that mimic low-rank factorization, an embedding layer, EF, of low dimension, and a linear layer, UF, that projects to high dimension. Thanks to this structure, the sample complexity is reduced by two aspects: by processing each field independently in its dedicated network, and by using low-rank factorization inside these field-wise networks. Our framework is also able to handle both categorical and numerical fields, and the internal structure of the field-wise network depends on the field type. Categorical fields are sparse and unordered, and therefore are represented by one-hot vectors, and then passed through the factorized layers. Numeric fields, however, are dense and ordered, and therefore are transformed to a nonlinear representation and only then passed through the factorized layers. Okay, so let's recap. FIFA learns high-dimensional per-field representations by field-wise factorized neural networks, then aggregates them by summing over the fields, passes through an activation function, and multiplies by output linear layer. We are now moving on to our empirical part. We compared FIFA to factorization-based models and neural networks on CTR prediction task and general tabular classification. We can observe that FIFA is effective in a wide range of cases, and therefore it can serve as a good drop-in for tabular classification tasks. Another observation from our results is that complex architectures do not seem to have an edge over well-tuned simple models as ours. We found that there are easier ways to gain performance improvements. As such, we obtain gains by choosing suitable width and activation, as well as tuning the regularization. We also conducted an empirical study on the advantage of using a GLU activation by examining two cases: a case where quadratic activation is preferred over ReLU, and a case where ReLU activation is preferred. We can observe that GLU provides consistently strong performance on both cases, so it's indeed a very robust choice. So, to summarize, in this work, we extended the connection between neural networks and recent factorization machines and presented a theoretically grounded neural framework for tabular data, FIFA. We showed that FIFA can automatically switch between popular methods by simply modifying its activation function. FIFA is also able to learn high-dimensional field-wise representations by low-rank factorization. Lastly, we provided an extensive investigation of our experimental design choices. And that's it. Thank you very much for your attention.
Thank you. So we have a couple questions on Slido. I guess a couple of them are sort of related to, how is FIFA in terms of memory consumption and compute?
So actually, we did not measure these in these aspects. We did perform an experiment regarding the runtime. We compared against a transformer-based approach, and we observed that the runtime is reduced by using FIFA. But memory consumption, we haven't tested, but it's a great insight. We can check it. And
Oh, excellent. And there's a somewhat related question asking, how does FIFA scale to sparse categorical features represented as one hot encoded vectors?
So FIFA can use for categorical, for sparse categorical features as done in CTR predictions, which are very sparse. I mean, we actually tested these kind of features, and we saw that the performance are really is even slightly better than the deep, wide and deep approach that we compared against. So it's totally there, and you can see more examples in our paper.
Oh, excellent. Thank you. Another question is asking or saying that factorization machines using fields are sensitive to field definitions and the features used. What features are used, and how are the fields defined in the current study?
I'm not sure that I understand the question, but if you mean that if you ask if we selected a subset of fields among the given fields, so no, we use all the fields in our experiments. If this was the question.
Okay. Excellent. And yeah, I guess there's one final question, which is just asking how does this compare against, or if you've done any studies comparing against XGBoost or Light GBM or any sort of like tree-based method?
Tree-based models. So yes, it's more related for the general tabular classification, and the focus of this work was to compare to neural architectures. We did conducted some experiments with regard to trees, but we did not focus on that. So I cannot come with any statement regarding trees. But overall, we know that tree-based methods are still outperform neural networks. So our results are slightly better or compared to neural and complex deep architectures. And this is the focus, to show that by selecting and focus on the activation and on the dimensionality of our framework, we can actually gain performance that are comparable to more complex architectures.
Oh, excellent. Thank you. So let's thank the speaker and and our